Hello viewers, in today's class we are going to discuss one important problem related to continuity and differentiability of a function, right? So here we are given a function f of x which is defined like this, and here we have the absolute value of x, and we have to test this function for continuity and differentiability at the point x is equal to 0, right? So let us start. So here we'll divide this problem into two categories. That is, the first we will test this function for continuity, right? So now from the definition of continuity, we know that a function f of x is continuous at x equal to a if the left hand limit and the right hand limit of the function are equal, and both these limits are equal to the value of the function at the given point, right? So this is the definition of continuity, right? Okay, so here we are given the point x equal to 0, so we may take this point a as 0, right? So now, before finding out the left hand limit or the right hand limit, let us first redefine this function, because here we have the absolute value of x, and we know that absolute value of x is given by positive x whenever x is greater than 0, and absolute value of x is 0 whenever x is equal to 0, and this is equal to minus x whenever x is less than 0, right? So now let us insert this definition in the given function. So now we can redefine our function f of x as see here we can write x e raised to minus c. Here we can write for mod of x we can write plus x, and here we have 1 over x. Here we have the positive x whenever x is greater than 0, right? And f of x is equal to x times e raised to minus 1 over minus x, because we are now taking mod of x is equal to minus x whenever x is less than 0, right? So here we have x less than 0, and our function f of x is equal to 0 whenever x is equal to 0, right? So we have now redefined our original function, and we can rewrite it as f of x is equal to x times e raised to, here 1 over x plus 1 over x is 2 over x, so we have minus 2 over x whenever x is greater than 0, and here we have see 1 over x and minus 1 over x, so these two get cancelled, and we have e raised to minus 0 which is 1, so here we have simply x, right, whenever x is less than 0, and f of x is obviously equal to 0 whenever x is equal to 0, right? So now to prove the continuity and the differentiability, we'll take this function, right? So now the left hand limit of the function f of x at x equal to 0 is given by limit x tends to 0 minus f of x, right? And here we'll now put x is equal to 0 minus h, where h is a very small quantity but greater than 0, right? So now the left hand limit is limit h tends to 0, because when x tends to 0, obviously h tends to 0, right? So we have here limit h tends to 0, and f of x, for x we can write 0 minus h, right? And now we have limit h tends to 0, and f of 0 minus h is f of minus h, and now we have limit h tends to 0, since we are finding out the left hand limit, it means we are approaching from the left of 0, right? See, here we have the number line and here we have x is equal to 0. So when we are talking about a left hand limit, it means we are approaching from the left of x equal to 0. So here for left of x equal to 0, we have x less than 0, so we have to take f of x is equal to x, right? So here we'll take f of x is equal to x for calculating left hand limit, and f of minus h is now equal to minus h. Here we'll take x equal to minus h. Now here h equal to 0, so this limit becomes 0, right? So the left hand limit is 0. Now to calculate right hand limit, we have limit x tends to 0 plus f of x, right? So this notation is for left hand limit, and this notation, that is positive sign, is for right hand limit, right? So now we have limit h tends to 0 and we have f of 0 plus h, because we'll take x equal to 0 plus h where h is greater than 0. X tends to 0 whenever x tends to 0, h tends to x tends to 0, h tends to 0, right? So I am writing here all the steps while calculating the left hand limit and right hand limit. So here we have limit h tends to 0, and this is f of h. And now see, whenever we are calculating the right hand limit, it means we are approaching from the right of x equal to 0. So here in the right of x equal to 0, all the values of x are greater than 0. So here we have to take fx is equal to x times e raised to minus 2 over x, right? So now we have limit h tends to 0 and we have h e raised to minus 2 over h, right? Okay, now this expression can now be written as limit h tends to 0 and we have h over e raised to 2 over h, right? Okay, so now if we substitute h equal to 0 over here, then we have here 0 and here we have e raised to 2 over 0, that is e raised to 2 over 0, that is e raised to infinity, and e raised to 1 over e raised to infinity is equal to 1 over infinite, that is equal to 0. So here we have 0 times 0, so we can write over here as 0, right? So now we see that the left hand limit and the right hand limit both are equal to 0, and moreover here the value of the function f of x at x equal to 0 is given as 0. So we conclude that the left hand limit exists and it is finite, that is 0. The right hand limit exists and it is finite and it is 0, and f of 0 is also 0. So these three quantities are all equal and finite, and in this case all these three quantities are equal to 0. Thus we can say that this function is continuous at x equal to 0. Now let us consider the differentiability of this function at x equal to 0. Now viewers, in order to test the differentiability of a function, we have to calculate the left hand derivative and right hand derivative, and if both the derivatives, that is left hand derivative and right hand derivative, exist, they are finite and equal, then we say that the function has a derivative at that particular point, right? So in order to test the differentiability, we have to separately find out the left hand derivative and right hand derivative. So let us first find out the right hand derivative. So the right hand derivative is given by limit h tends to 0 f of x plus h minus f of x over h, right? Sometimes the right hand derivative is also denoted by r of f prime of say here we have to test the differentiability at 0, so we have to write here 0. So r of f prime of 0 denotes the right hand derivative of this function at x equal to 0. So now we have limit h tends to 0, and here we have f of 0 plus h because the point x is 0, and here we have f of 0 over h, and this is limit h tends to 0 f of h minus f of 0 over h. And now here f of h, see we are calculating the right hand derivative. It means we are approaching from the right of x equal to 0, right? So we are approaching from this side, so we have to take f of x is equal to x times e raised to minus 2 over x. So here we have h times, because this is f of h, so we have h e raised to minus 2 over h, and f of 0 is equal to 0, and we have here h. So now we have limit h tends to 0, and this is h e raised to minus 2 over h, h and h get cancelled. This is limit h tends to 0, and we can write e raised to minus 2 over h as e raised to 2 over h, right? And if we take h equal to 0 over here, we get e raised to 2 over 0, that is e raised to infinite, right? And e raised to infinity is infinity, and this is 0, right? So the right hand derivative of f of x at x equal to 0 is 0, right? So we can write it over here. So the right hand derivative is 0. Now viewers, the left hand derivative is given by limit h tends to 0 f of x minus h minus f of x over minus h, right? And sometimes the left hand derivative is also denoted by the notation L of f prime of 0, right? So here we have the point x equal to 0, so we have limit h tends to 0 f of 0 minus h minus f of 0 divided by minus h, and we have limit h tends to 0 f of minus h f of 0 divided by minus h, and here we have limit h tends to 0, and now f of minus h, see we are approaching from the left of x equal to 0. So here we have to take the form of the function as f of x is equal to x, right? So f of x is equal to x would be taken in order to calculate the left hand derivative, because we are approaching towards x equal to 0 from the left hand side, right? So f of minus h is simply here minus h, f of 0 is 0, and here we have minus h. So now we have limit h tends to 0, and we have minus h over minus h, and this is limit h tends to 0 1, because these two get cancelled and we are left with 1, right? So viewers, here we see that the left hand derivative is equal to 1, right? And this is quite evident that the right hand derivative is not equal to the left hand derivative, that is 0 is not equal to 1. Hence we conclude that the given function, this function is not differentiable at x equal to 0, or in other words f prime of 0 does not exist. right? So this example once again it proves that all continuous functions are not differentiable, right? So viewers, all continuous functions are not necessarily differentiable, right? So this is how we solve this problem.